All right. Hello, everyone, and thanks for coming to the first PhySU Colloquium of 2025. And I guess let's just get straight into it. I'd like to welcome our speaker for today, Marty. He's a student in his third year in the Physics Specialist program, also the PhySU VP Academics. And today he's going to be telling us about some of the research that he did over the summer in Professor Kushner's group in atmospheric physics. And he'll be telling us a little bit about modeling the climate system.
Hello, everyone. Thank you for coming. It's nice to see you all. Still have a couple people coming in. Make sure you grab some refreshments, okay? We have cookies, the hard work of the Colloquium committee, okay, on display here. So we have tea. The English breakfast is pretty good, I will say. Twinnings makes a good English breakfast tea. So that's no milk, unfortunately. I apologize. It is what it is. Contact Umang. That's who's responsible. So what are we doing today? Modeling the climate system. What does that mean? What is the climate system? Well, there's two contexts, which I'm going to be discussing that today. Am I good, Dorna? Everything's good? Everything's going well? Okay, perfect. So there's two contexts, two types of, two ways I'm going to be using that word today. So the first thing I want to talk about is, in the context of understanding a lot of atmospheric phenomena, it's very powerful to deploy physical tools, especially a lot of thermal physics and the theory of, work and compression of gases and these sorts of things, to understand what is happening in the climate. So I want to go over a few of those today, talk about some large-scale atmospheric circulation, moist convection in the atmosphere, the greenhouse effect, and discuss how we can model these from a theoretical, a physical point of view to understand what's going on. But that's like a pen and paper kind of a type of a model, it's a little old-fashioned. And so then I'll discuss how, in order to actually make weather predictions and then these sorts of long time scale climate predictions, especially as it relates to climate change. It's very important. Anybody in this room is skeptical of the reality of climate change? We have a non-believer. Okay, Nathan, my promise to you, you'll leave this room. You'll be you and Al Gore, right, hand in hand, okay? That's what's going to happen. So we'll talk about some numerical models. I don't really know as much about the numerical modeling, but it's something I think is important to discuss. But if you have any questions, I probably won't be able to answer them as much in detail. I apologize. And then I want to talk about some of the work rolling after that into some of the work that I did this past summer and some that's still ongoing. Not as much producing those numerical simulations, but doing analysis on them. You'll see more of what I mean. But for the beginning, what do I have here? Okay, so I mentioned off the hop, I want to talk about some simple physical principles and how they're applied to understanding some simple atmospheric phenomena. So number one here, I have a plot. I have a plot from this book. Okay, this book, good book if anybody's interested, that describes the vertical temperature profile of the atmosphere. Now, because I have so few slides, really I would show this in like 4 minutes. So, I will explain why this is. But really, okay, here's the thing. You want to understand the atmosphere. The important part is this part. 80% of the mass of the entire atmosphere is here, okay? This is basically nothing. I mean, that's not obviously true at all, but, effectively, as far as we're concerned, we're really caring about this part. That's where all the hard stuff is going on. The rigorous, the moist convection, cloud formation, hurricanes, that's all here, okay? So this is, as you can see here, in numbers of kilometers. So it's just a very simple, and you can see here what's interesting is that as the temperature goes down, as the height increases, the temperature decreases up to this point when it goes back And so what's happening here is this is where ozone is in the atmosphere, something that's very important. The majority of the atmosphere is transparent to solar radiation. Energy comes from the sun, and it is mostly incident upon the ground. It passes almost completely through the atmosphere. And of course, the exception is ultraviolet rays, which are absorbed by ozone at the top of the stratosphere, where the boundary between the mesosphere and the stratosphere is called the stratopause. And the stratopause has a local maximum of temperature because of the absorption of UV light. And that, of course, as we all know, that the reason why UV light specifically is absorbed by ozone, it's all quantum mechanics. It's very important. But what I think is even more interesting is this right here. Why is it that there is such a strong bubble of heat right at the bottom? Okay, so as I said, let's take the planet, right? Let's say, of course, the Earth is locally flat, okay, and then we have layers of air, and then there's the sun. Okay, so let's say we're on the surface of the Earth. Now, as I said before, all the rays that come from the sun, except for the UV, basically all of them go right to the planet. Okay? So we get, right at the surface of the Earth, most of the energy the sun, the atmosphere above us doesn't absorb much of that at all. But, as we know from physics, there is black body radiation. And it turns out that although this shortwave, high energy solar radiation is transparent to the atmosphere, the longer wave black body radiation, which the Earth and which everything with heat emits, the atmosphere absorbs that bandwidth of light quite rigorously, or vigorously is the word I meant to say. So the Earth will absorb this light from the sun, get hotter, and then emit some of its own black body radiation. And then, of course, this layer of the atmosphere will heat up, and it itself will emit its own black body radiation in each direction. And so what occurs, this is the crux of the greenhouse effect. What occurs is that we absorb all the light from the sun and then give some of that energy back to the air above us. But because the air above us emits its black body radiation in every direction equally, we get some of it back. And there's this continuous effect where as you get further from the surface, more and more of this light is reflected back towards the surface as you go up. And it ends up being, off the top of my head, that the top of the atmosphere, oh well, there's that big spike at the top, but really, like, this is basically the top of the atmosphere, right? It's much, much colder, as you can see, than the bottom, okay? The reason at the top there, I think it's ionizing radiation in the high atmosphere, but there's very little mass above the mesopause, so that's not a very significant factor in terms of the temperature profile, in terms of the atmospheric dynamics which go on, like weather and, climate and all of this. So that's a pretty simple piece of it. I think the greenhouse effect is pretty well understood. But so there's another piece which is, important. I guess it's well understood that the ground is warmer than the air above, but I think, it's interesting to see why that happens. And of course, I think it's fascinating that it all just comes from black body radiation. Use the Stefan Boltzmann law for this. It's very simple. And there's another thing we use from thermal physics to describe moist convection. So what does that mean? Oh, well, I guess I'll go back a little bit. So we have here, okay, the planet, all right? Now, as in this model, okay, in this line graph here, you wouldn't expect a lot of convection. You wouldn't expect a very churning atmosphere, right? It would be pretty still. Now, typically, when you heat a liquid or a fluid from the bottom, oh, sorry, you're right, Dora. Now I'll stand here. That's better. No, you're good. You're good. When you heat a fluid from the bottom, you expect there to be an unstable density profile, right? When the denser fluid is on the top, you would expect that it will sink and the fluid below will rise. But there's an important condition here. Usually when you talk about this in a first-year physics class, you're talking about a water or something, which has a stable top point where beyond which there's no fluid pressure, okay? Or it's another fluid, right? In this situation, there's nothing above the atmosphere. It's space. So the density of the atmosphere must go to zero. And so there isn't that condition. It will always be that there is, I would say, lighter air, it would always be that there's, warmer air below the colder air. And you will always have this density profile. And it ends up being, I won't get into the exact details of why, but it ends up being that the Earth, the Earth's atmosphere is stable to some amount of this lopsidedness. You can have warmer fluid below colder fluid, and it won't cause an instability, and it won't cause that sort of convection. But, as we're all aware, there is instability in the atmosphere. There is weather and convection, okay? And there's quite a lot of it. So then why is this going on? Well, what we've described here is only a description of a dry atmosphere. But Earth has something which is very important. Earth has a lot of water. And the presence of liquid water in the atmosphere and the dynamics of cloud formation end up having very important consequences on the convection which occurs. So, back to the Earth, okay? So we have here, let's say, a low parcel. This is a piece of air, and it's pretty wet, okay? Let's draw a water droplet. Now, what's going to happen if we move this piece of cloud or piece of air up a little bit? Okay, as we've discussed, as air gets further away from the ground, looks like an eye, doesn't it? It's kind of funny, whatever. As the air gets further from the ground, it will cool down, okay? Now, another result from thermal physics is the Clausius-Clapeyron equation. Now, I bet you a lot of you folks didn't think this was going to come up, but it's actually very important. Because one of the consequences of the Clausius-Clapeyron equation is that the amount of water which can be held in air, okay, let's call this variable Q. The humidity of air is directly proportional, or is exponentially proportional to the temperature of that air, okay? So if we increase the height of this parcel of the atmosphere, the temperature of it will decrease, and the amount of water it can hold will decrease exponentially. And at a certain point, what will happen is that the amount of water it can hold drops below the amount of water it contains. And when this occurs, the water condenses, and this is what happens when we have cloud formation. So the cloud formation is a result of moist parcels of fluid of the atmosphere reducing in temperature, usually just a result of some perturbation. They're displaced upwards, probably some other piece of air pushes it upwards or something along those lines, right? The reason could be anything. There's always chaos and instability in the atmosphere. So this push upwards will cause it to cool, and that will cause a reduction in the amount of water it can hold and a condensation. This water will form into a cloud. Yes?
Are there ways you can push it upwards yourself?
I mean, a fan, I suppose, would probably do the trick.
I mean, like large scale to make clouds.
Yeah. Ask me at the end. It's pretty complicated. It's like there's a lot of geoengineering. There's something called marine cloud brightening, especially. but it's controversial. If you've ever seen Snowpiercer, similar to those. Okay, well, never mind. Ask me at the end. That's a good question. But we don't actually have to lift it ourselves, because what ends up happening, when this water condenses, it releases latent heat. And this release of latent heat in the parcel contributes to that unstable, or keep in mind, when I said in this context, when it's a shallow enough lopsidedness of the temperature, the vertical temperature profile, it is stable to dry convection. But if we introduce that latent heat, which is released by the condensation of water, it pushes it over the edge, and we can get conditions which are ripe for cloud formation. And so this is the takeaway here, is that all moist convection on Earth, all cloud formation, and clouds are pretty important, is a result of the Clausius-Clapeyron equation. So when Stephen Julian tells you it's important, it really is, guys. You got to pay attention, okay? Let's delete Sauron. And the third thing I want to discuss is going even bigger now. How does this play an effect on the large-scale heat transport and dynamics of the atmosphere? Okay. Oh wait, I've not been doing my. Oh, this is perfect. This is exactly the slide I should be on right now. Okay, so. Oh, you know, I'm a little far ahead. I can't go to that slide yet. So we have the Earth. Okay. Let's say the sun is here. Now, as we all know, everybody understands this. The equator is warmer than the poles, okay? And so, as we just learned, it's warmer. Also, we know that there's a lot of water at the equator. There's some oceans there, okay? So we should expect that these are ripe conditions for very moist air. And indeed, we see this. The equator has very moist air. And as we just saw, the more moisture you have in your air, the more it will occur that you have moist convection, and you have rigorous cloud formation in which parcels which are near to the surface will be lofted upwards by this release of latent heat. So it will occur that a moist parcel which is near to the surface of the planet at the equator will be lofted upwards by this process. In doing so, all of the moisture in it will condense and fall out as rain, and you'll have a dried, this is not to scale, you'll have a dried fluid parcel of air, that's the fluid. At this is about 10 kilometers up is where this happens. And you can see that here. Okay? So we have this occurring of near the equator, air is getting lifted upwards. This is the cool part. So, as we go from near the equator towards the upper latitudes, there is a decrease in temperature, right? The planet is facing more away. Obviously, this is more complicated, really, but you know, at a first order, the planet's face is away from the sun, and these will receive less radiation from the sun, and therefore they will be cooler. Okay, so what will happen as you have this, let's say, a horizontal band of air that wraps around the Earth like this, okay? Where this side is hotter and this side is colder. What will happen, okay, is that this piece of the parcel will be more, it will have a greater propensity to expand. And this expansion will cause it to push other gas poleward along this line, along this altitude, okay? And you get winds blowing from near the equator towards the poles at an altitude of about 10 kilometers. And this is all because of these same physics concepts I've described already. But, okay, now you have to think about it like this. We have the Earth rotating about this axis. Okay? We have a thing, right? A piece of the atmosphere which is rotating around at that distance from the Earth's axis. Then, because of these fluids, because of this, heat profile, it's going to get pushed and it's going to follow this path inwards. And keep in mind, it's rotating, it has velocity like this, okay? So it's going like that. Now, what do we know from angular momentum? If you're spinning around an axis and you move inwards towards that axis, what do you have to do? This is a call and response section of the presentation. Okay, you're spinning, you have your arms out, you're spinning in an office chair, you pull your arms in, what happens? You spin faster. So this piece of the atmosphere is spinning around the Earth's axis of rotation. As it moves inwards, it will spin faster. And so what you get, in order to spin faster, it has to pick up a portion of eastward velocity. This says westerlies, which means it's eastward. It's very confusing. And you will get a jet stream, which moves in this way around the pole. And that is all a result of this is all a result of conservation of angular momentum. Let me play a video of it for you. This is a simulation from NASA. What did that do? Okay, this one should work. I just say click on full slides, eh? Perfect. Yeah? No. So I think this is pretty cool. I don't know about you guys, but I think this is neat. I'll play it again. Do we have any questions? Yeah?
But it's not really precise gesture. It's possible that some of it will be caused by global warming, because some winds are blowing from the Atlantic, and then it created some sort of loose gesture. It goes to south instead of heading back to the North Pole.
Well, it's all caused by global, or not caused by, but it's all related to global warming. Part of the reason that it's like looping like that, it's making those sorts of motions. It has to do with something called the baroclinic instability. So what happens is, because of this kind of thing, okay. Should I turn the light back on? Can you guys still see me? No? This is better? Oh no, I think it's okay. We got a shake of the head when I asked that question, so I think people prefer the lights off. Just because you asked, I'll say this is a little bit in the weeds, but I'll go over it quickly. So because of this, you also have a vertical density or a horizontal density profile. So the density of the fluid will be a little bit like, the fluid will be denser here, and it'll be less dense over here, okay? And so if you look at this, what you can see is that if you rearrange the fluid, like if you took the heavy fluid here and you put it here, and you took the lighter fluid here and you put it here, you would get a lot more energy. You've just released a lot of gravitational potential energy from the atmosphere. Does that make sense, everybody? And the introduction, obviously, if you take away potential energy, you get kinetic energy. And the introduction of all of that kinetic energy into the atmosphere around this location causes a lot of strong winds. And so that's a big contributor. And the sort of chaotic nature of these dynamic situations cause those sorts of roiling motions. It's also, I believe, a result of the Coriolis force. But I don't remember exactly off the top of my head. Another?
It was actually what you were just talking about chaos. I was going to ask because it's unrelated to what you're talking about now, but you mentioned it. Like how the majority flow in that motion, but there are a lot of like stray, like other groups of that's attributed to chaos, right? Like there's no phenomenon.
Oh, well, I don't know. I mean, it depends on how you want to classify it. Really, you could say it's all phenomenon. I don't know. I mean, some of it is. There are a lot of really complicated motions which you can describe with a lot of, rigor or whatever. But, I mean, some of them nobody understands. And, you might just say that's chaos. I mean, sometimes a hurricane comes through where you don't expect it. And, I mean, who can say why it happened? I mean, So, to what you're saying, I mean, it probably is the case. There's all these little complicated motions that you could have never predicted because, one cold front advanced one place that you didn't expect it to because something else happened 15 years ago. It's so complicated, it's very difficult to understand with certainty, you might say impossible. Do you guys want to watch the video one more time or should we move on? What's the... Move on, okay. I get it. Wrap it up. Oh my gosh, we only have 20 minutes left. And this is... Okay, well, so that's the first part. Okay, so that's the first part of the presentation. So now, I hope everybody has an appreciation for the beautiful physics of the atmosphere, okay? I think it's really fascinating stuff. And once you start to appreciate these things, you really start to look. I mean, because, listen, I don't know if you guys noticed, but there's living things on this planet. It's such a perfect atmosphere. The conditions for life are so specific. And so studying the Earth, it's really fascinating because, you'll be reading along, right? And it's like, oh yeah, there was a 3 to 1 billion chance that this might have happened. I mean, the odds of it working out so perfectly are so low. I mean, all these things had to go right. We had to have just the right amount of air, too much carbon dioxide or too little carbon dioxide in the atmosphere, and we'd be cooked. We had to have just the right amount of ozone. Literally, just the right amount of ozone in the stratopause to make sure that all the UV light doesn't fry us. We have to have just the right condition in the core for the magnetosphere. And all of this, and it's not just one or two things, okay? There's so many things about our atmosphere that have to be just perfect for there to be life. I mean, of course, we don't know. Maybe life could have evolved with different situations. But for us, life as we know it, this is what we need, and we have it. It's incredible. It's an emergent, it's different than like, a fundamental field of physics where it's so specific and there's no reason why. It's basically all random chance that it happened this way, but there's an emergent organization which occurs, which is just right for life, and it's really, and of course life also contributes to the chemical composition of the atmosphere. But anyways, so as I said before, this is all well and good, Clausius-Clapeyron equation, but if we want to predict the weather, we have to actually bust out our computers and solve some partial differential equations, because this is fine, but nobody can solve by hand, exactly what's going to happen. The computers can't do it either, but they can get closer than we can. So, how then is large-scale climate modeling done? So generally, what they do is they have these system of equations for modeling the climate. Okay, so there's the Navier-Stokes equations. Everybody knows these. And they also there's equations which relate the amount of heat that you transfer in and out of a piece of the atmosphere. Okay. And essentially what you get is a massive system of about 6 or 7 partial differential equations which you have to solve for 6 or 7 variables, including, the temperature of air, the humidity, and all over the place, right? And this is just for the atmosphere. There's an even more complicated type of model which attempts to include and describe every piece of the atmosphere and how they relate to each other dynamically at each moment in time. So it couples the workings of the oceans to the workings of the atmosphere and the land. So, for example, how much snow is there on the land, right? The amount of snow, if it increases, that changes the amount of light which is reflected away from the planet, and this will change the temperature of the air. And all of these little feedbacks which the air and the atmosphere has with itself, okay? Very complicated. So usually what is done at a basic level is that we divide the Earth up into a bunch of little grid points, okay? Obviously this is along 2 dimensions along the surface, and then there's like a dimension upwards. So you might have a grid box that's like, 1 degree longitude by 1 degree latitude, and it's, a kilometer tall, right? That's a kind of a characteristic scale which you might have for one of these grid cells. And then they solve the equations along each grid cell. And keep in mind, if you're doing a coupled model, which relates different portions of the climate system to each other, you'll have many, many more than just those, a set of 6 equations. And it gets to be very expensive. But people want to know how bad climate change is going to be, so we do it anyways. So now I'll get into, over the summer, I was looking at some different sets of these coupled Earth system models, okay? So basically, each government of the Earth will commission a different organization to make one of these models, and sometimes there's more, like Canada just has one major modeling center, but the US, I think, has a few of them, and different modeling centers have different models which, focus on different aspects of the climate system, but overall, they're all very complicated and they're all pretty good. They all, for the most part, simulate the workings of the atmosphere at a very good level. So specifically, we were interested in this project in looking at snow, land snow. So these models also include, as I mentioned before, a land snow component, which looks at the amount of precipitation falling in an area, the temperature there, and a number of other variables potentially. And it will relate that and figure out how much snow is on the ground. But in order to make these models very accurate, we need very accurate and very widespread, both in time and geographically, measurements of the variable. And unfortunately, it's very difficult to measure snow. You have to go out into the forest and put a stick in the ground and measure how deep it is, and then take a bit of the snow and measure its density. And it's very difficult. It's very difficult. So, there's some satellites, but it doesn't really work. It's an area of uncertainty. And so because of this, there is a lot of uncertainty in the ensemble of land snow models, okay? And so we were looking and comparing these different data sets using something called the Brown Temperature Index model. So this is a very simple snow model, which essentially only takes in from a given data set the temperature and the precipitation. So this is not a coupled model like those other ones I was discussing, okay? It is just a simple computer program which will take in an atmospheric data set which describes the temperature and precipitation over a given period of time. And it will predict, as a time series, the amount of snow on the ground. And because this is so much simpler than the climate models which are produced, by these large organizations, it's very cheap to run. And you can end up producing a large number of snow data sets which are parallel to these large coupled model snow data sets, but using a different snow physics simulator. And so the hypothesis is, or what we're investigating is, if we have this number of, I think it was here, we're looking at 6 of them, right? If we have 6 Earth system models, each with their own temperature and precipitation data and their own snow physics simulator, what happens to the data set? How are we doing for time? Oh, that's plenty. We're good. What happens if we put in our own physics for the snow, but use this ensemble of temperature and precipitation data? So what we get are 6 data sets of snow which have different source temperature and precipitation, but the same snow physics. Does that make sense to everybody? It can be a little confusing. So we have a data set of 6 models with different physics of snow, and we have a data set of 6 models with the same physics of snow. And we're asking ourselves, how do these data sets differ from each other? One of the main pieces we use to compare is a snow region classification. Essentially, this divides the land up by what type of snow you expect there. And so we're going to be comparing how do these data sets differ region to region. Okay, so there's 6 of them you can see on the thing there. This slide is not important. Okay, so what do we find? This is just for comparison. Okay, so you can see the different colors represent the different models we're using. Okay, solid lines are coupled models. Dashed lines are simple models, which we produce ourselves. Okay, and this is a plot on the y-axis, snow mass. Okay, here. And over the course of a year, this is averaged across a few decades. Now, it's interesting when you look here, okay? It's interesting when you look here. So that was just plotted along an absolute value of snow mass. But if we kind of normalize the plots and we just look at the variability, you can see here that in regions where there's a lot of snow, like tundra and boreal forest, okay, there is a much more agreement between offline models and, basically across the board, there's much more agreement between models, okay? The uncertainty is much lower. Whereas if we go to a region which has not as much snow in it, like if we go back here, you can see maritime and ephemeral regions have very little snow. And you can see here they have much higher uncertainty. And this is not very surprising, of course. As I just mentioned, the more data we have, the better we understand a region, the better we'll be at modeling it. But where it gets interesting, okay, and the real application of the temperature index model is when we apply the model and then look at the deviation from the average of these ensemble data sets. And what you can see here is that in almost every case, in the large snow, in the areas of large snow, when we look at the data set with the same set of physics, it has a much lower variability. And so, using this, the theory is that we can attribute some of the variability. Let's say we ran all the data sets, using different temperatures but the same precipitation, or vice versa. We can attribute the amount of difference between the produced models in terms of how much do they differ because of precipitation? How much do they differ because they have different temperatures? How much do they differ because they're using different physics of snow in the first place? Okay? And also, look at how this is the maritime region. That's like I think it's mostly Alaska. A lot of it's the names aren't very good, but if you see here, there's not a lot of red on the map. It's mostly the Alaskan Panhandle and Norway, and it's really bad. I mean, the uncertainty in that region is very high. So there's also more analysis needed in that region. Okay, and so I think this is interesting. It's a statistical tool that we can use to better understand the sources of variability in an ensemble of climate data sets. And how are we doing for time here? So it's 5:51. Okay, You know, that's good. That's enough. I won't talk about what. Don't worry about it. If you want to ask me about what we're doing next, you can ask me about it. But that's enough talking. We'll open it up to questions at this point. So, okay, there we go. So that's the end of the presentation. Thank you. Thank you. Okay, any questions?
You can answer the clouds question.
The which?
The one where you can make clouds.
Oh, marine cloud brightening? Okay. Well, like, so basically, so some people want to do something called marine cloud brightening to help mitigate climate change. So the idea is, I mentioned that snow earlier. I mentioned that snow it's more reflective and therefore it reflects more of the sunlight away, and that makes the atmosphere colder, right? So that's called albedo, and clouds have a very high albedo. So the idea, in order for what I said about, the condition for condensation isn't the whole truth. Just water alone condensing won't be enough for cloud formation. You also need aerosols in the atmosphere, like, usually like dust or something, just a little bit for the water to kind of condense around and sit on when it falls out of the air, right? So the idea is, what people want to do is we inject a bunch of salt into the atmosphere in tropical latitudes in the ocean, and the theory is that this will make more clouds, and then more of the sun will be reflected away. But I mean, the thing is, we really don't understand what effects that will have. It might work, right? We don't know. So that's a way to make clouds, if that's one way, Or I mentioned this movie, Snowpiercer. I don't know who's seen this movie. Really? Oh, I don't think so. No. Well, anyways, don't worry about it. Oh, it is Chris Evans? Oh, okay. Yeah. It's a train movie. So what happens? This is a movie. I shouldn't have brought it up. I thought more people had seen it, but never mind. In that movie, in order to stop climate change, they inject like a science fiction molecule up high into the atmosphere, and then it basically causes like an artificial nuclear winter, and then the whole Earth cools down, and it's like a blizzard everywhere, and that's why it's called Snowpiercer. But that later part is, the point is that some people do want to inject aerosols high in the atmosphere to stop climate change from happening. But similar to the marine cloud brightening, it's a bit of a gamble. I mean, we don't understand, we just don't understand the system well enough. I don't know. 2030. There we go. Thank you, Evan. Another?
Yeah, but the aerosols, usually self-arising in the popular, temperature around days, doesn't really do much in the atmosphere. Usually, the one that harms a lot would be allergens, the CFCs, they destroy ozone. Because ozone actually melts into liquid under minus 80 degrees Celsius. So we see ozone depletion. It has much more effect, the allergen, instead of what you inject. The aerosols doesn't really last long. It reacts a lot.
I have seen that too. There's some research in the group about nuclear winter, and they have found that too. Yeah, it's surprising, but the aerosols from, like, most of the aerosol injection, which they think will occur from a nuclear war, is caused by fires which are set by the bombs, and then the smoke and everything goes up, and as you say, they have found that there isn't great longevity to those aerosols in the atmosphere. which is surprising to me. I don't know anything about chemistry, so you know better than me why. But okay. Any other good questions? Mm-hmm. Well, no, it's just a coincidence. Sorry, it's not. It's just because, well, it has to be warm here because of the greenhouse effect, and it has to be warm here because all of the ozone is absorbing a bunch of UV, and it has to be warm here because of there's like, I think it's like cosmic radiation that's in the space, or it's from the sun. I think it's probably more likely that it's. I don't remember exactly. I apologize. So it's just that there are those 3 periods where it's quite warm because it's absorbing some sort of radiation, and then other places it's not quite as warm because there isn't any of that going on. Yeah, it's not as simple, unfortunately. Uh-huh. Mm-hmm. You mean like this? Or like, do you want to come up and point? Like here? Oh, no, this here is depicting, so the poleward transfer, which is being depicted here, I mean, the answer is yes, it is a continuation of this motion, but it's not the same cause. It's not the horizontal temperature and density gradient that's causing these winds. It's a different effect, which is related to what I mentioned about the release of gravitational potential energy, which is caused by those. It's a different cause from the same idea of that there's some horizontal gradient in density. But it's also more of a turning motion. It's similar to the jet stream video we watched. So that motion poleward and backward. Please move. Don't tell me what to do. That's what sort of this up and down sort of motion is. Is that, you know what I mean? But it, of course, changes also with height and whatnot. Okay. Is that it? Okay, that's it.